Okay, so in class, what we did about a couple weeks ago, we were trying to look at the sampling distribution of the sample proportion. And what we did was that we were rolling dice and we were trying to see the proportion of even numbers that we obtained. So what we all did, we all were able to use a dot plot and plot all of our findings and our data. And what we found was that the proportions actually became normal. So what we're going to do exactly the same thing, but with the sample mean. So we will continue a little bit of this on Monday or on Tuesday. But I just want to give you guys a little taste of what exactly this is about. So let's say this is going to be my parent population. So this normal distribution right here, whoops, I don't know what I did. This normal distribution that I have here is my original population. So this is a set of all the possible observations. So what I'm going to be doing here is I'm going to be taking a small sample of this population and seeing what the means look like. So right now, if I look here, my mean is 16. So everything is centered at 16. The median is 16 also. My standard deviation is 5. Don't worry about the skew and kurtosis. Don't worry about that. Okay, so what I'm going to do, I'm going to take a sample, a small sample size of 5. So I got 5 observations from this original population. And after I got those 5, I added them together and took the mean of it, and that's what the blue one represents. So if I were to continue grabbing many different types of observations and getting the mean, well, what would the distribution of this mean look like? So if I keep doing this over and over and over and over again, eventually this will look like a picture. Now, what would the picture look like? Well, let's do this 10,000 times. Well, eventually what happens is that this picture looks very much like the normal distribution. And I can continue doing this for many different samples. So I can do this when n equals 10. I can get 10 observations from this population and then find a mean, and I can do this 10,000 times and I will still get a normal distribution. Now what happens is that the normal distribution starts to kind of get closer and closer together. I can do this with n equals 25, do this, and this is going to take a very, very long time because I'm taking 25 observations. I'm going to speed this up. This is what exactly is going to happen, okay? So I'm going to get something that looks like a normal curve, and yeah, that's basically all it is to it. So when we talk about the central limit theorem, we're looking for what exactly is x bar going to look like. So if you remember, x bar here is what we call my sample mean. Okay. We know that if we were to take the sample mean of if each and every one of you guys were to get some sample, maybe GPAs, ask certain people what their GPA was, and you took a mean and then you plotted it with everyone else's, most of your means are going to now look normal. So the sampling distribution of the sample mean approaches a normal distribution as the sample size gets larger. So in other words, x bar is normally distributed with, this is going to be the mean of the sample mean. This is going to be the standard deviation or the standard error of our sample mean. Okay, so this is very different. I'm going to write different than what we had before. This is where it was p hat normally distributed, p square root of p 1 minus p over n. Okay, so now this is our new distribution. Now we're going to look at x bar. We already did everything with p. Now we're going to do everything with x bar. Okay, so let me show you guys a couple of examples, and then we'll do a little bit more simulations on Monday or on Tuesday, depending on what class you're in. Okay. So here is my example. My example says, suppose that males' heights are normally distributed with a mean of 65 inches and a standard deviation of 4.2 inches. So if you think about this x here, let's say x is the male student's height. This is normally distributed with a mean of 65 and a standard deviation of 4.2. So this is something that we've done before. So what is the probability that a randomly selected male will have a height that is at least 63 inches? So if I were to draw a picture of this, okay, here's 65, and I want to figure out what is the probability that the height is at least 63. So if this is 63, at least is everything above it. Okay, so there's all of this. Okay, so that's basically the area that I'm looking for. Okay, so this is no difference. No, this is stuff that we've done before. This is going to be normal CDF. My lower bound is going to be at 63. This is going to go all the way to infinity. Okay, my mean is going to be 65 and my standard deviation is going to be 4.2. Okay, so now let me put that into my calculator. So second data, I'm going to go ahead and look at normal CDF with my mean of 65, my sigma of 4.2. My lower bound is going to be 63, and I'm going to leave my upper bound like that. Okay, so my answer is going to be 0.683, about that. Okay, so there is about a 68% chance that this randomly selected male will have a height that is at least 63 inches. Okay, so that was nothing different than what we've done before. It's just using a regular normal CDF. Okay, now let's say now I got 25 male students, so I choose 25 students. What is the sampling distribution of the sample mean? Okay, so let's say I wanted to figure out the mean of the mean height of these 25 male students. Now the distribution is going to change. It's no longer going to be this part. It's not going to be that. Now it's going to be something different. Now it's going to be X bar. X bar corresponds with sample mean. This is just sample mean. This is going to be normally distributed with a mean of mu and a standard error of sigma over square root of n. So everything is going to be the same. The only thing that's different now is that, well, mean, okay, well, this is the same thing. This is still the 65 inches. The only thing that changes is just the standard error, because this is going to be sigma. Sigma was 4.2, and I'm going to divide it by the square root of n, which in this case was 25. So my sampling distribution is going to be 4.2. So let's take 4.2 and divide it by the square root of 25, which is 5. And what I get is 0.84. Okay, so now everything has changed. My sample mean has now been normally distributed with a mean 65 and a standard error of 0.84. Okay, so now here's my question. Use a sampling distribution, so this thing, okay, use this to find the probability that the mean weight, so notice here, look at this word, the mean weight of the 25 students will be at least 63 inches. Notice that this one is very different than part A. Part A, we're still looking for at least 63 inches, but we're looking for a randomly selected male. Whereas here, we're looking at all 25 males that we got, we're adding them to their height together and dividing it by 25. And what we're gonna get is try to get their mean height. I just noticed this should be say height. Their mean height should be at least 63 inches. Okay, so one of them is just looking for any randomly selected male. This one we're looking for the 25 students. Okay, so what are we gonna get? So we now have our new sampling distribution. The mean is still the same, it's still 65. Okay, we're still looking at 63. So this is still the same, 63. We still are looking at least. Okay, so nothing really has changed. So still normal CDF, right? My upper bound, my lower bound is still 63. My upper bound is still going to be infinity. My mean now is still 65, but my standard error is now going to be 0.84. And this is very similar to what we had, because notice that before it was 4.2, but notice that as we got more samples, if we look at the simulation, this thing actually got it shrunk. The normal distribution was really fat before, and now it's really skinny. So now what we're gonna do, we're gonna go back here. We're gonna do the normal CDF. So let's go ahead and do it. Second data. Normal CDF, 65. Now we're going to change our sigma to 0.84. This is going to be from 63 all the way to infinity. And what we're going to get is a really large probability, 0.9914 approximately. Okay, so the probability that the mean height of these 25 students will be at least 63 inches is about 99%, which is almost likely. Okay, all right, and that's basically all it is. We'll continue talking more about it, but something to really note make sure that at least you know this for now, okay? Because this might show up on the quiz, something like that. Maybe you might have to write it down. Okay, so that's just basically it for the central limit theorem for means. I wanted to give you guys a little taste of what's to come.